Okay, our last problem in chapter 24 deals with the same kind of quantitative nuclear chemistry themes that we've been seeing, but kind of applying it to a more interesting case. So applying it to radiocarbon dating. So the same equations that we've been talking about are still going to be relevant. That half-life equals 0.693 over K. And then the natural log of what we start with what we end up at time t is going to be proportional to the amount of time that's passed and the rate constant. But again, this time we're using it to talk about the ratio activity between, say, an organism while it was alive with the remains of an organism after it's died, and ask the question, how much time has passed since that organism has passed? So looking specifically at the problem, they talk about the charred bones of a sloth in a cave in Chile represent the earliest evidence of human presence at the southern tip of South America. So they have a sample of the bone, and it has a specific activity of 5.22 disintegrations per minute per gram of carbon. Now again, those are the units. That seems kind of strange, but remember, units of activity really don't matter, because what we're really doing is we're just comparing the ratio of two activities. And we're saying for whatever that ratio is, it's going to be proportional to the amount of time that's passed. So for carbon dating, what we look at is we look at the C12 to C4 ratio for something that's living, and then we compare that to the ratio after something has died. And the ratio of what's left is going to be proportional to how much time has passed since that organism died. So it might be easiest, again, if we put all of our given information down, and we can see where we're at. So we're given that any organism that's alive is going to have a C12 to C14 ratio. So again, just an activity of 15.3 disintegrations per minute per gram. The remains of our sloth has an activity of 5.22 disintegrations per minute per gram. So again, we're given the activity at the onset, we're given the activity after a certain amount of time has passed, and as long as we know the proportionality constant, the rate constant, we can figure out how much time has passed. Well, they do give us that the half-life is 5,730 years. And again, we can use the equation that we have here to relate the half-life to the rate constant. So rearranging this, the rate constant equals 0.693 over t1/2, and then we can get the rate constant for a half-life of 5,730 years is 1.21 times 10 to the minus fourth per year. So now we have our rate constant, and we're going to be solving for how much time has passed. Now again, just to highlight, we use this for carbon dating, but it can be used to date a lot of other things using different isotopes. And the premise is the same. You're looking at the ratio of activity between the start of something and where you're at right now, and then asking the question, how much time has passed to get to this ratio? So I'm going to take this equation right now, and I'm going to solve it for the variable that we're interested in, which is how much time has passed. So that's going to be equal to the natural log of a sub 0 over a sub t. And again, k being in the denominator, I can represent that the same way by going and just saying 1 over k. So putting in the pieces of information that we have here, t is equal to the natural log of the ratio with what we started with. So any organism that's alive is going to have a carbon 12 to carbon 14 ratio with 15.3 disintegrations per minute per gram. And the remains of our sloth have an activity of 5.22 disintegrations per minute per gram. And then 1 over k is going to be 1 over 1.21. Whoops, 1.21. 1.21 times 10 to the minus fourth per year. And just as a little side note here, if we have 1 over year as our units, that comes out as years. So t equals the natural log. If I take the ratio of this, it's 2.93103. 1 over this very small number is 8,264.4 years. So t equals the natural log of this number is 1.07535 times 8264.4 years. So the time that's passed after we take the number from our calculator and do a little rounding, is about 8,900 years. So let's do a kind of a quick ballpark check and see if that makes sense. So if one half-life had passed, we would have expected the activity to be half of what it was, so about 7.15. We can see that it's less than that, but it's not the equivalent of going through 2 half-lives, because that would have been half of 7.15, which would have been like 3.6 something. So we're not that small, so we're somewhere between 1 and 2 half-lives, and our value is somewhere between 1 and 2 half-lives. And always keep your, kind of logic hat on. If you got something that was a really, really small number here, that wouldn't make sense to say that that sloth was, for example, 8.9 times 10 to the minus 4th years. That's a really small number. We're talking about radiocarbon dating something that's been in a cave that documents the earliest evidence of human presence. So use your logic hat and see if something makes sense. And just kind of a little side note, as you're working through quizzes or exams, if you work through a problem and you get mathematically an answer that doesn't make sense, but you don't have time to go back and fix it before the exam period is up, just write a little note saying, I really don't see where I messed up. This answer doesn't make sense. You're likely to get more partial credit for letting me at least know that you understand that your answer doesn't make sense.